Hi, I'm Dane Quinn from the University of Akron, and today's video lecture will cover degree of freedom. So what is the degree of freedom of a system? Well, essentially it's the number of independent motions that a system can undergo. More concretely, it's the number of independent coordinates that are required to uniquely specify the configuration of a system. So configuration here means where the system's at. And I've got three examples here. The first is a block sliding down a plane. Right? So really the motion is just along the plane. Now I realize that the block moves left and right and up and down, but the minimum number of coordinates would be 1 to specify where this block is on the plane. And we could use the distance down the plane. Let's call it x. So if I tell you where the block is, essentially I'm telling you what the value of x is. So here this would be a 1 degree of freedom system. And notice that we abbreviate degree of freedom DOF. Now if I look at a second example, let's look at a bar that's pinned at one end and rotates. So again, different material points are moving in different ways, but really we just need one coordinate to describe the location of this bar, and that coordinate could be theta. So if I tell you this angle, the inclination of the bar relative to the horizontal plane, then you can tell me exactly where the bar is. So again, this is a 1 degree of freedom system. We only need a single coordinate to describe where it's at. We can have more complicated systems, right? So now I have a disk, and that disk is going to essentially roll and move along the plane. So here I might need actually 2 coordinates, right? So one coordinate could be, say, the angle theta, and the second coordinate could be the position of the center of the block, right? So let's call that x. So because again the block can move left and right, and it can also rotate. Now there are some cases where these two things are tied together. So if this disk rolls without slip, then we have a constraint. In particular, the horizontal displacement to the right, x, is minus r times theta. This is our common rolling constraint. So the fact that these two coordinates are constrained means that I only need to know one in order to determine the other. And as a result, this would be a 1 degree of freedom system. However, if the blocks, or if the disk slips, then the displacement in the horizontal direction is no longer tied to the rotation of the disk. So x is not equal to minus r theta. And in order to uniquely specify the configuration of the system, so really that means where every single material point is, I would need to know both the horizontal displacement of the disk and then its angle of rotation. So now if it slips, this would actually be a 2 degree of freedom system. So depending on the constraints of the system, we can have a different number of degrees of freedom. And here I'll just give some more examples. If I look on the left, I have a link, right, so that has fixed length. And if I ask, where is the position of point P at the end? Well, it could be anywhere on this circle. So if I tell you this angle, theta 2, you could tell me where this point is, right? What's the position of P? And so this would be a 1 degree of freedom system. So now, if I look at this second picture over here, I've taken a small link and pinned it to the end of the first link. So now I have 2 links, the blue link, which I'll describe with theta 2, and the dark gray link, which I'll describe with the angle theta 3. So now in the light gray region here, This is all of the potential locations of the end of this second link. Here, again, P. So if I were to describe the vector from, say, O, the origin, to P, and I'll describe that as P with respect to O, then this point can be anywhere in this light gray region. And I've kind of shaded some other configurations here and here. And I need two coordinates to describe the configuration of this system, or in particular where this point P is. So now this would be a 2 degree of freedom system. Those two coordinates could easily be theta 2 and theta 3. But those aren't the only two coordinates I could use. There you could come up with any combination of coordinates that might describe the configuration of this system. Right. So here, each link adds degrees of freedom. To the overall system. However, each constraint removes degrees of freedom. So if we're asking what's the degree of freedom of the system, right? Well, you have to take into account the number of links and the number of constraints. So in particular, here we have one link, we have one constraint, namely this pin joint at the center. Over in the second example, I have two links, and I have now two constraints. I have the pin joint at the center, and then I have the pin joint between these two links. Right, so there's this balance of degrees of freedom added by the links and degrees of freedom removed by the constraints. Because additional links do not necessarily add degrees of freedom. It depends on also the constraints in the system. So here we actually have two links, and then I've added a third link in red, and I've pinned it to the ground again. So this is actually a 4-bar linkage, something that we'll consider a lot in this class. And it just so happens that this is a 1 degree of freedom system. So even though I added a link, I also added, well, we had 2 constraints as given in the previous example. I actually added 2 more constraints. I added a pin joint between this gray link and the red link, and then I added a pin joint between the red link and the ground. So here I've kind of shaded different configurations, and you can kind of imagine how this works. If this light blue link spins around, right, so it traverses this circle, then the red link kind of rocks back and forth. Again, this is a 1 degree of freedom system. So if we want to estimate the degrees of freedom, again we have to look at the number of links and the number of joints or constraints. So each link that we introduce adds 3 degrees of freedom. Right? So here, let's say this light link here is the starting point, and then I move this link over to this new position here. Right? So basically P moves to some new position P prime. Right, so that would be the displacement of P, position of P prime with respect to the starting point. And then it could also rotate, right, so I might need an angle theta. Again, we'd have 2 coordinates associated with this position, or this displacement vector, and then a third coordinate associated with the rotation. So again, links in general that are unconstrained have 3 degrees of freedom. So each constraint that we have, and we also refer to these as joints, removes degrees of freedom from the system. So let's first look at a pin joint. This is the one that we've seen before. Pin joints allow 1 relative degree of freedom between objects. So the way to think about this is that we have these 2 links that are connected by a pin joint. imagine if the dark gray link is fixed, right? So, or maybe we just know its location. And then we ask, how many relative degrees of freedom does the light gray link have with respect to the dark gray link? Well, in this case, it's 1. The only thing this link can do is really rotate about point A, right? So maybe we would need 1 coordinate to describe the orientation of this light gray link with respect to the dark gray link. So again, this is a 1 degree of freedom joint, and we refer to these as J1. Right? Essentially, this removes 2 degrees of freedom. Right? Because remember, links start off with 3. This ends up with 1, so we've taken 2 degrees of freedom away with this pen. Now, the other one that we'll look at commonly is a sliding joint. So here we essentially have a slot in this dark gray link, and then we have a second link, light gray, that's allowed to move in the slot and then rotate. So this allows 2 relative degrees of freedom. Between these 2 objects. And so it removes only 1. And here maybe we would measure the displacement along the slot, and then we could measure the rotation of the link as our 2 coordinates needed to describe the configuration here. So again, we see a 1 degree of freedom joint and a 2 degree of freedom joint given in these 2 examples. So we can use this to estimate the number of degrees of freedom from the system. And we do that based on this thing called the Kutzbach criteria. And essentially it amounts to counting up degrees of freedom. Right? So the total degree of freedom of the system is 3 times the number of free links. So we'll say n minus 1. And n is the number of links and we always include the ground. We think about the ground as a fixed link. So this is the total number of links or degrees of freedom associated with the links, because the ground has no degrees of freedom. We assume it can't move. And then we'll start subtracting off degrees of freedom for the joints. So J1 is the number of 1 degree of freedom joints. So those were pen joints. Each one of those removes 2 degrees of freedom, so we have 2 times the number of joints. And then let J2 be the number of 2 degree of freedom joints. So those were like slider joints. And each one of those only removes 1 degree of freedom. So we have the total number of degrees of freedom associated with the free links. And again, we throw the ground in there, so that's why we have the n minus 1. Minus the number of degrees of freedom removed by the 1 degree of freedom joints, minus the number of degrees of freedom removed by the 2 degree of freedom joints. And again, the degree of freedom refers to the number of degrees of freedom that remain after you apply the constraint. So let's look at these 2 examples. Right, so here we again have essentially a 4-bar linkage. We'll call the ground link 1, we'll say link 2, link 3, and link 4. Right, so these are the 4 bars of our 4-bar linkage. So n here is equal to 4. Now, the number of constraints, let's do that in green. Right, so we have 1, 2, 3, 4. So we have 4 1 degree of freedom joints. Right, so J1 is equal to 4, and I have no 2 degree of freedom joints. So J2 here is equal to 0. As a result, when I go and calculate the degree of freedom, it's 3 times 4 minus 1 minus 2 times 4 minus 1 times 0, which is 1. So this 4-bar linkage is a 1 degree of freedom system. And we saw that in this previous example. This was also a 4-bar linkage, right? And we had already said it was 1 degree of freedom. So now let's look at a second example. And this is called a slider crank. Notice that this constraint here essentially is a sliding joint between the ground and this red link. Right? So this whole thing is precisely a 2 degree of freedom joint. Right? So again, let's count things up. Right? We have 1 link for the ground, we have 2, we have 3 links total. Let's count up the number of 1 degree of freedom joints. Well, we have 1 there, we have 2 there, and then let's count up the number of 2 degree of freedom joints. Well, we have just 1 there. So N is equal to 3, J1 is equal to 2, and J2 is equal to 1. So the total degree of freedom is 3 times 3 minus 1 minus 2 times 2 minus 1 times 1. And we work all this out. It's a 1 degree of freedom system. Right, so both of these are 1 degree of freedom systems. 4-bar linkage and slider crank. These are 2 very common mechanisms, and we will study them a lot, which is why I started off with this. Now we can also use this for more complicated examples. Here I have, kind of a weird looking mechanism. So let's estimate the degree of freedom. Well, count up the links, right? We have 1 for the ground, 2, 3, 4. This whole thing in red is 1 linkage, 5, and 6. Right? So here N is equal to 6. Let's count up the number of pin joints. 1, 2, 3, 4, 5, 6, 7. So here J1 is equal to 7. And we have no 2 degree of freedom joints. Right? So J2 is equal to 0. Calculating the degree of freedom, we get 3 times 6 minus 1 minus 2 times 7 minus 1 times 0, which turns out to be 1. This is a 1 degree of freedom mechanism. I only need to know 1 coordinate, so maybe the angle of this input link, to describe the configuration of the system. Right, so now let's look at another example. And this one I'm going to do actually in 2 different ways. So the first way, we'll recognize this as a 2 degree of freedom slider joint. So again, counting up the number of links, we have 1 for the ground, 2, 3, 4. Right, so here N is equal to 4. Number of 1 degree of freedom joints, 1, 2, 3. So J1 is equal to 3. And the number of 2 degree of freedom joints, is just 1. So J2 is equal to 1. So calculating the degree of freedom, we have 3 times 4 minus 1 minus 2 times the number of 1 degree of freedom joints minus 1 times the number of 2 degree of freedom joints, and that becomes 2. Right, so this is actually a 2 degree of freedom mechanism. Right, so I would need to know 2 things in order to describe the configuration. One of them could be, say, the input angle of this blue link, and maybe the displacement of the slider. Now, one question that often arises is, well, can't I consider the slider as another link? Well, the answer is yes. Right? So a second way of doing this would be, and I'm gonna write the differences here in green. Right? So the second way is to say that this is an additional link. If I were to treat the slider as an additional link, then suddenly n would be equal to 5. Right? Because I have 1, 2, 3, 4, and then 5 for the number of links. But notice the constraints then change. I would actually have j, well, let's count them up first. Right? So the number of 1 degree of freedom joints. Remember, these allow 1 degree of relative motion. So 1, 2, 3 as before. But now this joint between the red and the yellow link would be a 1 degree of freedom joint. So that would be joint number 4. And the constraint between the slider and the ground, well, that would only allow 1 degree of freedom of motion, because you can't move this slider left and right, and it can't rotate. So that would actually be another 1 degree of freedom joint. So in this case, J1 would actually be equal to 5. And J2 now is equal to 0. So when I work that out, I get a degree of freedom of 3 times 5 minus 1 minus 2 times 5 minus 1 times 0. Well, once again, I get 2. And I really should. The degree of freedom of a system is a property of the system. It should not depend on how I choose to count things. Right? It should just be something that's fundamental to the design of that linkage. So again, if you want to break this slider up into an additional link with an additional sliding constraint, then you end up with 2 extra 1 degree of freedom constraints together with an extra link, but the degree of freedom of the system is the same. Right? So, like I said, depending on how you think about sliders, right, you can do this. You can calculate the degree of freedom in a couple of different ways, but ultimately you get the same answer because the degree of freedom is a property of the system. So some more kind of special cases. What if we have coincident joints, right? So what if we have a link, or we have 3 links that all come together at a single pin joint, right? So these coincident joints connect multiple link pairs. So a link pair might be between blue and red, between red and gray, or also between gray and blue. So it turns out that this is a 1 degree of freedom linkage or mechanism. You can kind of think about this as 2 slider cranks, right? So one is sort of here and there, and then maybe there. Right, so this would be a slider crank mechanism. But we also might have another between here and there, and then kind of the way to describe this link is like so. Right, so basically I have 2 slider cranks that are put on top of each other. So because they're both driven by the same link, essentially it's a 1 degree of freedom linkage. But if you were to simply count up the number of constraints and treat this as 1 pin joint, the criteria wouldn't work out. So the way to really think about this is to say that imagine that this coincident joint is actually split apart. Right? So I'm going to take it and put these 2 things close together. right? But I'm going to put a pin joint between the blue and the red, and then I'm going to put a second pin joint between the red and the gray. And the idea is that as these two things get closer and closer and closer, right, we recover this picture on the left. So now let's again count links. 1 for the ground, 2, 3, 4. I'll treat these as 2 degree of freedom joints. So the number of 1 degree of freedom joints, well, we have 1 there, 2, 3, and 1, 2 for J2. So again here, n is equal to 4. J1 is equal to 3, and J2 is equal to 2. Now calculating the degree of freedom. Degree of freedom is equal to 3 times 4 minus 1 minus 2 times 3, 1 degree of freedom joints, minus 1 times 2, 1 degree of freedom joints. Right, so here we have 3 times, well, 3, 9, minus 6, minus 2. So this would be, again, a 1 degree of freedom mechanism. But if you counted this constraint only once, well, essentially, you'd only have 2 of these, and you'd get the wrong degree of freedom. Right, so whenever you have these coincident joints, right, you have to kind of virtually spread them apart, and then look at the link pairs. So now, the last thing is this criteria can fail. It's not an exact calculation, but it can fail when the system is either over or under constrained. Right? So an under constrained system would be, an example would be here. Right? So imagine you have these 3 legs, and they're of equal length, and you have the upper link, which is the same distance as the distance between these 2 outer points. So now this system has a lot of symmetry. Right? It turns out that this is a 1 degree of freedom mechanism. Essentially, these 3 legs all do exactly the same thing. The upper and lower links remain parallel, right? But if I just start calculating, I have 1 for the ground, 2, 3, 4, 5 links total, so n is equal to 5. The number of pin joints, 1, 2, 3, 4, 5, 6. So J1 is equal to 6, and here J2 is equal to 0. So when I calculate the degree of freedom, again, the degree of freedom is actually equal to 1, but that's not equal to what we get using our criteria, which is 3 times 5 minus 1 minus 2 times 6 minus 1 times 0, which ends up being 0. So our criteria would predict that it's a 0 degree of freedom mechanism, but in actuality it's a 1 degree of freedom. And again, really it's because of the symmetry in the problem. If any of this symmetry was broken, then this would in fact be a rigid mechanism. It would only have 1 degree of freedom, right? So if you took this somehow and moved it over, right, you changed anything at all about this and broke the symmetry, it would revert back to a rigid system, right? So 0 degree of freedom mechanism. Systems can also be over-constrained, right? So I can have essentially too many constraints, right? So this linkage here it's a 0 degree of freedom system. And let's calculate everything again, right? So we have 1 for the ground, 2, 3, 4. Right, so n is equal to 4. Number of 1 degree of freedom joints. Well, we have 1, 2, 3, 4, 5. All right, so J1 is equal to 5. J2 is equal to 0. There's no 2 degree of freedom joints. So when I calculate the degree of freedom of the system, right, I should get 0, but I don't. Instead, I get 3 times 4 minus 1, right, again, number of links, minus 2 times 5 minus 1 times 0. This actually ends up as minus 1. I don't even know what minus 1 degrees of freedom is, but that's what we predict, and it's not right because the system is overconstrained. The way to think about this is that actually I could replace any one of these pins between a link and a ground with a slider, which would only remove 1 degree of freedom, and it would still be a rigid system. Right? So actually adding extra pin joints means that I've overconstrained the problem. And that's why this ends up failing. So, a couple of examples where it doesn't work, but in general, the Kutzbach criteria is a very useful way of quickly estimating the degree of freedom of a linkage. And except for special circumstances, when we have symmetry or possibly overconstrained systems, this really does a good job predicting the degree of freedom of the system, which can help us when we go to identify equations that ultimately describe the kinematics of these linkages. Right, so that's our lecture on degree of freedom. Thanks, and I will talk to you again. Take care. And then I ask, how many coordinates do I need to describe this light gray link? Well, I'd really only need 1. Oh my goodness. What was that? It's like the Loch Ness Monster. Or between objects. You did it again! Well, I think I'm going to start this one over again. What, you just woke up and decided to do that? You guys have thrown me off.